We looked at a ring counter to generate timing signals. Now we'll look at a type of switch-tail ring counter called a Johnson counter. It's a combination of a shift register and a decoder to generate timing signals. So that switch-tail ring counter, what we'll see is it feeds back Q prime from the last flip-flop into the last stage of the ring counter into the first stage of the ring counter. And that gives us a few more states available for the same number of flip-flops. So if we look, for example, here, all these flip-flops can be reset to 0 asynchronously. So we don't need to worry about loading one with a 1 and the other with 0. So but we do need to start with an initial state of all zeros. If we start with that state, what's going to happen is E prime is what gets shifted back into A here, our A flip-flop. So then we'll get a 1, 0, 0, 0. And after that, we'll get this 0, E prime will get shifted back in, we'll get 1, 1, 0, 0. And that's our third sequence. And then we'll get 1, 1, 1, 0, our fourth sequence. And finally, we'll end up with all ones in the registers. And then what we're going to, what's going to come back here is E prime, so we'll get a 0. So we'll get 0, 1, 1, 1. And this sequence will repeat itself. Once we get to 0, 0, 0, 1, we'll come back around and we'll get 0. So we have 8 unique states of this flip-flops, this switch-tail ring counter as designed, as long as there's no noise or something to get an unknown state into one undesired state into one of these flip-flops. So these are our 8 state sequences. If we were going to look at the timing sequence for that, here we see this is actually a uses QD as the output, but switching Q calls it QD, switches that back around, and that's going to repeat. So if we look at our 4 timing waveforms, we have timing waveforms where each of these signals is high for 4 cycles and low for the next 4 cycles, but where their rising edge is 1 cycle away from each other. So we have 4 cycles of rising edge and then 4 cycles of falling edge. So we could get 8 unique edges doing that. However, what we could also do is get 8 unique signals. To do that, we need a decoder. So to get a decoder, we'd have to decode these states. So if we're going to decode these states, how would we decode them? Well, we could say, for example, that the state 1 is A prime, B prime, C prime, E prime, right? And we could it's the and of all those. But perhaps we can simplify that by figuring out where are these unused states. So if we mark the unused states, we have unused states here in state 4 is not used, state 5 is not used, or binary 5. State 2 is not used. We have an unused here, 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 right, and here. So in all these binary combinations are not part. There's 8 binary combinations that are not part of the switch-tail ring counter. So as long as we don't get into an unused states, we could use those, for example. So if we were going to design, for example, our sequence number 1, well, that's in state 0, 0, 0. That 1 goes here. Well, if we use those unused states, now we just end up with our A-E prime, right? So instead of A prime, B prime, C prime, E prime, we can just use A-E prime. So we can do that for each of these states, right? So if we look, for B here, for B it's 1, 0, 0, 0. So we could circle down here. We have A, B prime. And you should make sure you understand how you can put these in the Karnoff maps. Make sure you understand where the unused states are. But this is review. We should know how to do this now. And we can decode these each to just one AND gate. The inverted outputs we can get from the flip-flops. So now we can get 8 decoded states. These 8 decoded states, again, we can find them with the Karnoff maps, or we could recognize them with patterns, of the regular pattern. So this here is this diagram we showed earlier. That's a CD4022B. It's a Johnson counter that you can get as an IC. It uses NOR gates as the decoder instead of AND gates. If you recall, our NOR gates use less transistors. So here it shows at the output where we want G0. At G0, which we designed to be A prime E prime from our Karnoff maps, well, we can convert that to A or E prime or A or E naught, and this showing the NOR gate, this symbol for a NOR gate, which is an invert OR instead of an OR invert, and it's pulling A and E as opposed to A prime and E prime. And you can verify for each of these NOR gates represent the ANDs that we decoded earlier. So that's how we can use this Johnson counter to create 8 unique timing signals. So where we have each of these timing signals just has a pulse that's 1 clock period, and that 1 pulse clock period, and then it's low for the other 7 clock periods within the within our cycle, and then it goes high again. So it goes high every 8 clock periods, and we could use those rising edges. So make sure we understand how this timing diagram, typically, if we look back here, the outputs to this IC are just G0 through G7. We don't end up with outputs. We don't end up with our QA, QB, QC, and QD. We get the decoded outputs. Now the disadvantage of this switch tail ring counter is if we do get into an unused state, we get stuck there. So we can look at that. If we get into state 0, 0, 1, 0, our next state, remember we're just shifting this 1, we're gonna the 0 comes back around and becomes a 1, and then this 0 shifts, this 0 shifts, and this 1 shifts, but then we shift around again, we get a 0, 1, 0, 0, this 0 becomes a 1, and then this 0, 1, 0, this 0 shifts around, becomes a 1, 1, 1, 0, 1, this 1 shifts around, becomes a 0, 1, 1, 0, 0 shifts around, becomes a 1, and then 0, 1, 1, and then the 1 shifts around again. We get a 0, 1, 0, 1, and then we shift around again. We get a 0, 0, 1, 0, and oh, look, we're back to the start. So basically, we go from 2 to 9 to 4 to 10 to 11 to 6 to, what's that? Oh, that's 11. In any case, and then we shift back up, right? So we go like that. So it has its own unique set of states. So that's a problem. We don't want to do that. We're not decoding for that type of sequence. So we need to have a fix for that. So, our fix for that is to put this little fix in here where we have the input to our C flip-flop is A or C ANDed with B. So that's a fix. Why does that fix work? If we look here, whenever B is equal to a 1, if A or C is equal to a 1 here, right? In either case, we want the next state of C to be a 1. So we can just fix it by doing that, and that will fix our problem with the unrecoverable status of this switch tail ring counter if we unfortunately get into one of the unused states. So our Johnson counter, it uses N flip-flops. If it has N flip-flops, we get 2 to the N timing signals. So we get twice as many timing signals as just a regular ring counter. So 2 to the N, 2 input gates are also required as decoders. Those decoders are, of course, it's the output of the flip-flops. Not as good as just using the outputs of the flip-flop, but we have 1 gate between that and the output of the flip-flops. So we can design within one IC to make those timing signals. We want to make sure that those timing signals have nice smooth edges. You don't want to have a little glitch on our rising edges. So we end up, instead of just T0 to T3 for 4 flip-flops, we end up with T0 all the way through to T7. So we get 8 of these rising edges. So that's the Johnson counter. I'll make sure you understand and are able to use that.